Hi, on the workbench today, I have an inexpensive pocket oscilloscope from FNIRSI. The model number is DS215H. It has two oscilloscope channels with 250 megasamples per second sampling rate and has up to 50 MHz bandwidth according to the specs. Of course, we have to test that out later in this video to see if the claims are accurate. Anyway, it is very compact in size, as you can see. Banggood sent in this unit for me to review. At the time of this recording, the price was just above $75, so that's quite affordable. Anyway, as usual, I will provide a product link in the video description below for those who are interested in getting one after watching this video. As a pocket-sized oscilloscope, obviously it is quite small in size. And of course, it's using these infamous MCX connectors, as you can see here, that I'm not a big fan of. Now, I understand why FNIRSI uses these because BNC connectors are just so much bigger. They probably would have taken up a lot of valuable real estate on the PCB. Now, FNIRSI does include an MCX to BNC adapter in the accessories. And speaking of which, here are the accessories. You can see here we do have a P6100 100 MHz bandwidth probe, which should be sufficient for the 50 MHz bandwidth of the scope. Now, we do have two channels, so it would be nice if they included two probes instead of just this one. At the very least, they should have included another BNC to MCX adapter. As you can see, we do have one included, as most people probably don't have a spare one lying around, so if you misplace the adapter, you are pretty much out of luck. By the look of it, you also get an MCX to alligator clips cable and a USB cable for charging and also connecting to your computer. Anyway, just to put the size of this DS215H into perspective, here I have a MiniWare DS213, which I reviewed a while back. Now, you can see that the MiniWare DS213 is even smaller than the DS215. In every dimension here, you can see that this is actually quite a bit smaller. Now, this is not really a direct comparison between the FNIRSI DS215H and the MiniWare DS213, as the specs for the DS215H is much better than the MiniWare. You can see here that FNIRSI has clearly borrowed or copied a lot of the design elements from the MiniWare. And you can see from the top layout here, the buttons are relatively the same, and also even the printouts here. And on the side, you can see that we have these MCX connectors. The layout and the spacing are also the same. The only major differences are these dual encoder design. Now, the designs are very similar, but FNIRSI had chosen to put the encoders on the side versus on the top on this MiniWare. Here I have a DreamSource Labs DS40252 I reviewed a while back, and it's slightly larger than the FNIRSI DS215, but it is actually using the standard BNC connectors, and the MCX is actually dedicated for the signal generator. Of course, the 40252 is considerably more expensive than the FNIRSI. Anyway, with the size comparison out of the way, let's actually power it on, shall we? Of course, the screen protector is still on. Let's remove that first. And by the way, I just dimmed the light in the lab a little bit so that hopefully you can see the screen a little bit better, as it's just super reflective here. I almost forgot to show you that the DS215H also has this stand on the side. You can actually pull it out and put the oscilloscope on your workbench like this. So hopefully this angle shows up better on the camera. All right, let's power on. As you can see, the boot up screen looks exactly the same as many of the FNIRSI products I have recently reviewed. My understanding is that you can customize the boot up screen by loading your own image. Now, I'm not sure why you would want to do that, but in case you want to, you can. Now, to adjust the scope is actually not that intuitive, as we only have a few buttons to work with, and the device does not have a touch screen. You can see that you can't touch it, but you can use these buttons to navigate. So let's give it a try. For example, let me actually zoom in a little bit so we can see it better here. And by the way, the buttons on top all have dual purposes, which can be activated by either a short press or a long press. Let's actually put in the signal first so that we can see the controls in action a little bit better. And I just hooked it up to the O1 DGE 2070 at the back there. You can see here. Right now, the output is off, so we are seeing some mains interference here, but let me turn on the signal generator first. Right now, the signal generator is set to 1 kHz output with a output amplitude of 1 volt peak to peak. Of course, we're over range right now, so let's actually auto-acquire that signal. And we do have a dedicated button for auto-acquisition, and that's the button marked A and C2. So this one is duplexed between the auto-acquisition and channel 2 settings. Anyway, let's press that. And currently, because we have both channels enabled, it actually separated out the channels here and put channel 1 on top and channel 2 at the bottom. And now you notice that the color scheme is not your default. By default, obviously, channel 1 is usually yellow, channel 2 is cyan color. That color scheme is industry standard. I don't think there's any reason for any manufacturer to change that. Anyway, right now we have 2 traces. Let me actually turn off channel 2 so that we don't get distracted here. And later on, we'll turn it back on. So let's see how we do that. And I think I need to long press this button. By the way, the camera is in the way, so my hand here is a little bit awkward. So let me press channel 2 here, long press. And you can see we can turn it off. So now it's off. And let's do an auto acquisition again. Yep, that is our 1 kHz signal. You can see here, the measured frequency is 1 kHz, and the peak-to-peak voltage is 1.02, which is pretty much the same as what we set on the signal generator. To change the vertical sensitivity and also the horizontal, all you need to do is use a combination of the button up here and the 2 scroll wheels here. You can see here right now, the indicator here is a V, that is to change the vertical sensitivity, and also the horizontals can be changed by this scroll wheel. So that's fairly intuitive. If you press the C1 again, you can see that it changes to positions. So now you can actually move the waveform around. Now you notice right now the waveform is moving quite slow. And when you press, I think press the OK button, I believe, and you can change it to move in a coarser fashion. And if you press it again, you'll go back to this fine-tune mode. And similarly, you can use the other scroll wheel to change the triggering position here. And let's press it again. Now you can see we can actually change the trigger level. And press it again, back to vertical and horizontal. So the controls here does take some getting used to. The vertical sensitivity can be adjusted from 10 millivolts per division up to 10 volts per division. The minimum sensitivity is not that great, especially if you have a ×10 probe. The peak voltage is rated at 400 volts. I assume that's for the ×10 probe. And that is actually good, as you should be able to measure mains waveform, even in areas with mains voltage up to 220 volts. You can also do on-screen measurement. Now, the way you do it is not as easy because we don't have as many buttons, but nevertheless, you can do that. So let me show you that. So I think I short press the menu here. Yep, you can see here we have additional menu items. And let's see what is this. The first one is actually for measurement display. You can see here, let me press OK. Now you can see these are the currently selected values. Of course, you can select others. Let's not look at that here. Let's go back and let's take a look at the next. Next, I think is you can save. Yep, you can save the current waveform, which is nice. Of course, it takes forever. So let's go back. The next one, this is where the cursor is. So let's take a look at that. So the cursor, let's say we wanted to do the time cursor. So we change it to the first one, X1, X2, we hit OK. So here, in my opinion, is where the design could be better. As you can see here, now we have to be able to move the different cursor positions. How do we do that? Well, we can do that, but in order to change the position of these 2 cursor lines, we have to actually exit the menu. And it's not just exit one level, we have to exit this menu all the way. I'll show you here. So we have to go back. Let me see how we do that. We press menu again. We press menu again. Yeah, now is only when we're in this mode, we can actually change the cursor position. And to change that, we have to also come back here to press channel 1 till we see X1, X2. Now we can actually use these 2 scroll wheels to change the cursor positions. So that's actually a little bit convoluted. All right, for the time being, let me actually remove the cursors and we'll get back to some of the other functionalities a little bit later on. So to get rid of the cursors, again, is multi-step process. We come back to the menu here. Now you can see it's getting a little bit tedious. So we hit OK, we hit OK again, and now we turn off the cursor. Of course, we have to go all the way back. And now let me actually increase the frequency on the function generator a little bit and see what we get on the screen here. 2 kHz, and you can see here, we're increasing. Now you can see that we are starting seeing some artifacts here. That's not great. Right now we're at 14 kHz. And again, you can see that this is definitely not output waveform, but nevertheless, we're seeing some of these artifacts. And whoa, you can see here at around 24 kilohertz, again, we're seeing some kind of a weird waveform here. And let's keep increasing. Of course, now we're aliased. You can see here, the frequency is 47 kilohertz, which is indeed matching what we're outputting from the function generator. But right now, the timescale is actually incorrect because we're still at 500 microseconds per division. So let me acquire that signal again. And right now, you can see that the timescale changed to 20 microseconds per division, and we are able to capture that signal again. Now, unfortunately, we have seen the same kind of artifacts on many FNIRSI oscilloscopes I have reviewed on this channel before. The sampling algorithm doesn't seem to have been implemented correctly on these scopes. And right now, you're looking at an amplitude modulated signal. The carrier frequency is at 100 kilohertz with a modulation frequency of 1 kilohertz, and the modulation depth is 100%. And you can see that we can sort of see the envelope, but we're not able to get a stable signal. Now, to be fair, AM signals are difficult to trigger on, even some of the more expensive oscilloscopes having problem getting a stable signal. After playing around with the settings, now I am able to somewhat stably capture the AM signal here. And now I just changed the carrier frequency to 1 MHz, still keeping that 1 kHz modulation, and the modulation depth is still at 100%. And right now you can see that we're barely able to capture that amplitude modulated signal. And I can adjust, let's say, the verticals, the horizontals, it doesn't really matter. And you can see here, I can sort of see the modulation going on here, but I'm not able to capture the signal stably. Of course, I suppose what we can do is we can change the modulation frequency a little bit. So hopefully the envelope gets in view here. So let's do that. So let's do modulation frequency, do 2 kilohertz, 3 kilohertz, 4 kilohertz. Yeah, you can see that now we are able to see the modulation again. But at 1 kilohertz modulation frequency, you can see that regardless of how we adjust the oscilloscope, it is very jumpy and very difficult to see the actual modulated signal. Now, of course, AM signals are not the easiest to capture, but this scope definitely has some limitations as well. And here we're looking at a frequency modulated signal with the same 1 MHz carrier frequency. The modulation frequency is at 100 Hz with a frequency deviation of 100 kHz. And I would say that it captured the signal reasonably well. The advertised bandwidth is 50 MHz. So let's see if we can actually hit that claimed bandwidth. Right now, I just removed the modulation and the signal coming in is still that 1 MHz signal. You can see here, right now, the peak-to-peak value is roughly still at 1 volt. So let's use that as a reference. I'll keep increase the frequency and see at what point we drop below that 3 dB mark. Let's actually see if currently the horizontal is at the lowest, as I do want to make sure. Okay, so let's change it to 20 nanoseconds per division, and let's increase the frequency here. So now I'm at 10 megahertz, and you can see we're still holding that amplitude. So let's do 20, 30, no problem. At 30, now we're dropping back to 1 volt, 40, and now we're at 940 millivolts, as you can see here. Also, the waveform becomes a little bit wobbly here. 50, that's the bandwidth limit, and we're still above 800 millivolts. So from this perspective, we are actually able to hit that 50 megahertz bandwidth claim. Now, you can see here the quality of the captured waveform is actually deteriorated quite a bit as it's wobbling back and forth. But at least for a single channel operation, we're able to hit that 50 megahertz bandwidth claim. So let's actually keep increasing the frequency here and see what the situation is like. Now, let me do that 1 megahertz at a time. 51, 2, 3, 4. Yeah, you can see that the amplitude started dropping. Now we're at 56 megahertz. You can see still the frequency counter is able to pick that up. 57, 58, 59. At 59 megahertz, we drop below the 3 dB line, and right now we're only getting a roughly 700 millivolts amplitude. So for all intents and purposes, for a single channel, I think 60 megahertz is probably the maximum you can go. Of course, we can still increase it further. Let's do 70 megahertz. So if you're really pushing it for a single channel, you can probably push it to 60, 70 megahertz, but you can see the signal quality definitely had deteriorated significantly. And that's a test for a single channel. So now let me actually enable channel 2, and the frequency right now changed back to 50 MHz, and let's see if we are able to display this waveform after I enable channel 2. So to do that, I'm going to long press here, and I'm going to turn on channel 2. And you can see as soon as channel 2 is enabled, let me reacquire the signal. Yeah, we're not able to view that waveform cleanly anymore, and you can see this is wiggling all around the place. Clearly, we're not able to capture that 50 MHz signal. So let's drop the frequency a little bit. 40. At 40, you can barely see it. 30. Yeah, I would say that once you have the second channel enabled, you probably are looking at maximum 30 MHz bandwidth. So this actually is an indication that the front end is sharing the same ADC. Once you enable the other channel, you can see that the bandwidth dropped essentially by half. And just for curiosity, I hooked up my avalanche pulse generator to channel 1. And I was actually not expecting it to be able to capture the waveform, but you can see that it was able to capture something on the screen here. So the front end actually is fast enough, at least, to be able to trigger on the avalanche pulse. Of course, we're not able to get a stable waveform. Nevertheless, the capturing circuitry is slightly better than I thought. The DS215H does support single shot. Now, that is a little bit hit and miss, and I had played around for quite a bit. I think I got it to be able to trigger. And let me reset it. Let's see if we can reproduce it. And for this test, I have hooked up a power supply, and let me re-trigger it. So let me power up the power supply. Yeah, you can see that we are able to trigger on that signal. And I have to say the setup is quite convoluted. It took a lot of time for me to set it up. And you can see here, if I come back to the trigger, you can see right now we're in single trigger mode. And you have to adjust the horizontals and verticals, and everything has to be set up just right. And I think the implementation has some issues because if the timescale is, for example, too low, it wouldn't be able to trigger on the signal. Now, according to the manual, the storage space of the scope is 14 meg. I'm not entirely sure how that translates into the supported memory depth though. As a dual channel scope, the DS215H does support XY mode, and let's take a look at that. Right now I have two 1 kHz 1 volt peak-to-peak signals coming in to both of the channels. So let's actually take a look. To change it to the XY mode, I need to come to the main menu here. By the way, there's still a couple of items I haven't touched upon yet. So for instance, this one here, we can do mathematics of these two signals. Let's actually take a brief look. So you can see we can do signal 1 plus signal 2, signal 1 minus signal 2, so on and so forth. Let's actually just do signal 1 plus signal 2 here. So you can see that the calculated waveform is displayed in the middle, and this actually can be quite handy. And let's come back here. So this one actually you can adjust the trace characteristics. What I mean by that, if you go in there, you'll see that you can actually adjust the afterglow. And this is potentially useful if you are observing a transient signal, which we're not going to look at here. So this is where we change it to XY mode. And bingo, you can see here, we already have this circle displayed. Of course, we can adjust the XY mode to make sure that it's centered. So let me do that. Okay, I managed to get the display centered, and it actually took quite a bit because you can see here, let me go back here. The reason is I have to align them in the oscilloscope mode. For whatever reason, I could not do that in the XY mode as I couldn't get to channel 2. And I think that might just be an implementation bug. Definitely FNIRSI needs to take a look. Anyway, right now we have the two signals. You can see here, these two are largely in phase and the same frequency. We, of course, get a circle. So now let me change the frequency of one of the signals. And you can see that we are able to display the characteristic Lissajous figure. Of course, if I change one of the frequencies, let's change it to channel 1. And if we change one of the frequencies, you can see that we can get different figures. And of course, you can see the Lissajous figure is a little bit sparse, and that's because it's also dependent on the sampling rate. And at this sampling rate, given the frequency we're putting in right now, this sampling rate is not ideal, and that's why you don't see a continuous line here. But nevertheless, the XY mode works as expected. And I do want to briefly show you the built-in signal generator. The signal generator on the DS215H is actually relatively rudimentary, and it doesn't have a lot of bells and whistles. And you can see here it's actually always on. Right now I just plugged it in to an oscilloscope, I haven't even done anything yet, but you can see it's already on. So to get to the signal generator menu, you just long press this M button here. And you can see we're in the signal generator mode. The first thing you will notice is that the output actually has an offset. It is DC only. It starts with 0 and output to about 3 volts. And that is something you need to pay attention to, as for example, if you're thinking you're just outputting a sinusoidal as an AC signal, and if you don't have a blocking capacitor, you could potentially damage the equipment you're testing. Anyway, that's just a side note. So here we have a few different waveforms you can select from. For example, we can change it to the different waveforms. And again, these are fairly rudimentary. We only have a few parameters to play with. You can see here. These are the different signals, but we don't have a lot of parameters. So for example, on the sine wave, you can select the frequency, you can select the amplitude. Let's actually give it a try. So let's come here to, let's say, frequency. How do we change it? And I think we need to press OK. Yep. Now you can see here, changing the frequency is actually not that easy. So we can use this scroll wheel to change the different digits, and we can change the frequency. But the maximum is actually up to only 50 kilohertz only. So let's actually take a look here. 30. So that's 50 kilohertz. Let's take a look at the signal. Yeah, the quality looks fine. So it's quite limited. And let's take a look at the amplitude here. Yeah, it is continuously adjustable, but nevertheless, the maximum is only at 3 volts. All right, with reviews out of the way, let's open it up and take a look inside. Well, pretty much as I expected, all the major chips, the markings have been removed. Unfortunately, we don't know what they're using. But this chip here is a Goldwind chip. I think that's actually an FPGA. And I just removed the shielding can. You can see the input section is fairly standard. We have a 4051, that's a MUX, and we have a couple of 8092, those are the op-amps. And that's pretty much it. Of course, we have a trim pot on each channel to fine-tune the frequency response. But overall, though, I have to say the layout is very clean and the board is pretty well constructed. Although we don't have any markings on the chip, we can clearly see that this must be the ADC chip, as is shared between these two channels. Of course, we don't know which ADC they're using, but nevertheless, that confirmed our suspicion earlier that the ADC is indeed shared. And if you look down here, you will see that the signal generator output is directly from this chip, and this must be an MCU of some sort. But you can see the output circuitry is fairly simple. So I'm guessing that they're utilizing one of the decks on the MCU and directly generating that output. And that also explains why the output is only capped at 3 volts. And you can see, actually, the scope draws quite a bit of current. During operation, it's drawing over 600 milliamps. Given a 1.5 amp hour battery, the runtime would be around 2.5 hours. As a pocket-sized oscilloscope, the FNIRSI 215H is pretty rudimentary. You should have no problem observing basic signals though. But for complex signals, I probably wouldn't trust what's being captured. With that said, this is more or less what I expected for a $70 scope. Let me know what you think in the comment section below. I hope you liked the review. If you enjoyed it, please remember to give it a big thumbs up and don't forget to subscribe to this channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.